Stefan is based in Berlin, Peter in Bayreuth, München now. Yeah, and we will hear about the new development. So, GraphHopper.
Yeah, I don't care. Okay, I can use both.
Maybe not, because then you get problems again.
Okay. Yeah, I'm Stefan Schröder from GraphHopper, and first of all, I'd like to thank you, the organizers, for giving me the opportunity to talk about our work. And let me first introduce you to GraphHopper. So what is GraphHopper? GraphHopper is a fast and flexible directions API. It is a lightweight API to solve heavy routing problems. And it all started when Peter Karich published an open source project called GraphHopper in April 2012. And it is basically a point-to-point routing engine based on OpenStreetMap. And I myself published an open source project called JSprit, and it is a toolkit to solve vehicle routing problems. And in April 2015, we joined forces, and since then, we've been developing our commercial product, the GraphHopper Directions API. And the Directions API basically consists of 4 parts: the routing API, the metrics API, which does many points to many points routing, the geocoding API, and the route optimization API. And before I dive into the route optimization API, I'd like to talk about the differences between the routing and the optimization API. And the routing API solves least cost path problems, that is point-to-point problems. For example, the least cost path from location A to location B. And it can also deal with several locations if you specify the sequence of these locations in advance. But once you don't want to specify the sequence, you need an optimization API so that the algorithm can decide about the best sequence. And our optimization API works as follows. We first geocode the incoming request. That is, we assigned geocodes to addresses. Then we snap these geocodes to networks. Then we calculate end times and travel times and distance matrices. And then we optimize the optimization problem, or we solve the optimization problem. And the problems we solve with the optimization API are usually called vehicle routing problems. And I just put a very simple definition of the classical vehicle routing problems here. Given M vehicles with capacity restrictions and customers find vehicle routes that serves each customer such that the overall transportation costs are minimized. And there's a huge variety of vehicle routing problems, and a specific form of the vehicle routing problem is the traveling salesman problem, where you only have one vehicle and no capacity restriction. And it is basically about finding the best round trip of a given number of locations. And these problems occur basically everywhere where people, services, and goods are moved through space. For example, these problems occur in last mile deliveries of food. They occur in the healthcare industry, where nurses need to make home treatment and visit patients, where disabled people need to be picked up and transported to their work, and then they pick up again and need to be transported to home again. And these problems occur in garbage collection, and also when technicians need to visit their customers. And the challenges, and what is challenging and interesting in these problems at the same time, is that the search space, that is the number of possible routes, increases very fast with the number of locations. For example, if you have a 50 location traveling salesman problem with asymmetric travel times, then the number of possible routes amounts to a faculty of 49, which is a number with 63 digits. And since the search space grows that fast, visiting the entire solution space is no option anymore. And therefore, mathematicians and operations researchers developed methods to provide exact solutions without visiting the entire solution space. And these methods are usually based on branch and bound and branch and cut principles. But as the problem size grows, also these options are not tractable anymore, and therefore they developed heuristics that have proved to find very good solutions within short time. And the most prominent heuristics in this field are, for example, taboo search and simulated annealing, and various algorithms that are inspired also by biology, by nature. And behind the GraphHopper optimization engine, we use the ruin and recreate principle, which is a large neighborhood search and which combines elements of threshold acceptance and simulated annealing, and basically works as follows. It starts with an initial solution, and then in subsequent iterations it removes part of the solution and reintegrates the removed locations again. And this is done by various ruin and recreation strategies, so that we go through the promising parts of the search space. But I don't want to go too much into the details of optimization. I just want to show you the variety of problems we can solve with our optimization API. And for this, I introduce you to our route editor, with which you can model, which lets you easily understand our API, and you can use it to also debug your solution. And for the following problems, I randomly selected 50 locations in and around Berlin and set one depot. And each location demands 1 unit of something. And I assigned 5 vehicles to the depot. And in the first problem, I assigned them sufficiently high capacities, such that a single vehicle can basically serve all customers. And this is basically a traveling salesman problem. And you can see this nice round trip. And in the second problem, I refined the traveling salesman problem and added a relation between 2 locations. And my additional requirement is that location 37 or location 38 needs to be served directly after location 37. And so the algorithm optimizes the problem subject to this additional restriction. And then let's turn the traveling salesman problem into a vehicle routing problem by reducing the capacity of each vehicle. And I reduced it to 20, so that we need 3 vehicles here, and this is the solution of these 3 vehicles. And to add another relation, in this example, I add the additional requirement that location 8 and location 16 need to be in the same route. And given that location, the algorithm optimizes the vehicle routes. And in the next example, I completely changed the objective function from minimizing the overall transportation time to minimizing the maximum completion time, so that each customer can be served as fast as possible using the available resources. And this gives 5 routes which are more or less balanced also when it comes to the operation time. And let's change this again and change the profile from car to foot, and we have another solution. And this is only an excerpt of what the optimization API can solve. We can solve problems with time windows, with driver skills, with driver brakes, with multiple depots, with multiple capacity dimensions, and so on. And this already brings me to the last part of my presentation, and here I'm talking about the experiences, or what we recently experienced with 2 blog posts. And the topic of these 2 blog posts were basically to find routes through Dublin. And the first blog post dealt with finding the shortest route through the city center of Dublin by avoiding all pubs in Dublin. And this is quite challenging since Dublin is known to have a very high pub density. And so we retrieved all pubs via Overpass Turbo from OpenStreetMap, and we configured the GraphHopper routing engine to consider this avoiding pub constraint. And as a reference, this is the fastest path from the green marker to the red one. And as you can see, it is almost impossible to cross the city center without passing by any pub. So you need quite a significant detour in comparison to the fastest route. And when it comes to the publicity, it was quite okay. We had a handful of retweets and less than 100 blog readers within 2 days. And we got the pointer that there was actually recently a Japanese man who tried to visit every pub in Dublin, to visit 226 pub to drink a pint of Guinness in each pub. And so we reformulated the problem and we searched for the shortest route through Dublin, visiting all the pubs. And this is a completely different problem. So the first one is a least cost path problem, and this is a traveling salesman problem with entirely different properties. And we came up with this nice round trip. And the round trip takes by foot 38 kilometers and almost 5 days, considering that it takes 30 minutes in each pub to drink a pint of Guinness. And what was interesting here was not so much the solution, but the publicity we got. So we got many retweets from all over the world. Almost 3,000 readers. We were on Reddit. We even managed to be a day on the front page of Hacker News with 84 points. And I just put some of the tweets here on this slide. And my favorite one is, perhaps I shouldn't confess this, but I have visited 26 Dublin pubs in 1 day. And yeah, and other nice tweets. GraphHopper tackles the problem of visiting every pub. The ultimate pub crawl. These guys figured out the best route for having a Guinness in each of Dublin's pub, and so on. And we were thinking about the reasons of these different successes. And one reason might be that the traveling salesman problems is slightly more interesting than the least cost path problem. And another reason might be the timing of the blog. But I personally think that the most important reason was the beer. And because in the first blog, we find routes that avoid pubs, so boring, nobody cared. And in the second one, we yeah, we find, as I said, we find routes that visit all pubs. And this is quite interesting because it tells us something about the role of the beer in our culture. And we were drawing the conclusion that if we want to maximize the visibility of our blog post, we need to wrap our technical articles around a beer story. So thank you very much for your attention.
Yeah, hi. I'm impressed you solved that problem. Very interesting. I was just going to ask you about what exactly are you, and what's your business model if somebody wants to use your API, like a company. Does it cost anything? And what's the difference between the open source JavaScript library that you put out and what you're offering as a service here?
So first, the GraphHopper Directions API is a commercial product. You can, we offer a hosted and self-hosted version of this commercial product. And if you go for a hosted version, then you can, you can subscribe for various subscriptions, and it depends on your demand. And the demand is measured in terms of requests and in terms of the complexity of the problem. And when it comes to the open source projects, you can still use these open, and we plan to still maintain both open source projects, but this costs money, and we find it a good idea to get this money for that by our commercial product. But if you are a developer, for example, of a location-based service, then you need routing. And you have, I think, 3 options. You can do it for your own, you can use Google, and you can also use GraphHopper. And maybe there are also other options.
What does the open source code, the other way around, what does your
it's a combination of the optimization engine and the least cost path engine. You can puzzle it together for your own, but you can also go the smooth way and the easy way to let us integrate both projects for your routing.
Thank you.
So thanks very much. I think we need to push a bit. It was a good talk. We had the next one from Johan. It's from Mapbox also, of the Berlin one, or you come together also, I'm not sure. So Mapbox, or I think also Konstantin was here also. We have later also an announcement which is also connected to beer, but it's something that we have learned that it's a good idea.
Hello.
But this is at the very end, something for the evening later on. But we have downloaded it as PDF, remember? We have just downloaded it.
But then we don't have nice animations.
Try again. This is again, one thing is with just, yes. The alternative, you just switch with CartoDB and we'll try later. You set up your own computer?
So the Wi-Fi just broke down, or?
I'm not sure now. Otherwise, I just suggest we take your presentation first from CartoDB, and you prepare it. And here we have it on as PDF.
It would actually be way more interesting if it has an internet connection.
Yeah. Are you online then? But you have no adapters. So who's an laptop now?
Does somebody have an adapter for VGA to?
Yes,
okay.
Hero.
Awesome.
So you got it.
No,
I guess the internet. Yeah, different technologies, different connections. So I'm not sure if the Wi-Fi is generally not working, or is it just because of this computer is not so much used? I think it works, doesn't it? Yeah. What's about the loudness now? I switched a bit. It's getting better.
Hello? Yeah, okay. It's like a guitar microphone, right?
For the afternoon, we have to switch it a bit higher.
Okay.
So sorry about this change, and we switch.
No, much. Oh, there is no connection. Okay. Oh, hold on. Actually,
That's why I said I like the PowerPoints. No, that sometimes are also very good animations, and this is not possible with PDF and PowerPoints. And maybe we take a minute, and then it will work.
sure. Okay. Here we go. Good.
Yeah.
Right. That sort of does it.
It looks good.
Right.
Thank you.
Hello. Sorry about that. I'm Francisco Dans. I work for CartoDB as a rendering developer. And my talk is called CartoDB and the New Spatial Technology Paradigm, which is a title that I did not choose. And I actually like the one that is in the bottom, New Ways of Exploring and Explaining Data. So for those of you who don't know CartoDB, I'll spend some time talking about our company. We're a geospatial company that is based in Madrid. We were founded as a spin-off of a visualization company called Visuality. It's okay, the sound? Cool. It started with a series of projects by Visuality as a consultancy that later evolved into a product to import data from any source and turn it into a visualization. So this is the sort of the three branches of services that we provide. We have a connection location data systems. So we have a set of tools for people to import the data in several ways. If you need to visualize your Instagram pictures, we have a connector for Instagram. If you have a company that uses Salesforce to locate the clients and manage them, we have a connector for Salesforce. If you just need to drop your table, or you want to connect your database to CartoDB and visualize your data, we have that too. You don't need to have even coordinates. We have a geocoder that will turn the addresses and IP addresses and all that stuff into coordinates for you to show them in a map. Okay. Well, that's the first part. Then there's the visual data discovery, which when all of that data is imported into CartoDB, we have the tools, both in client and in the server, to turn that into very, very beautiful visualization, which is what I'm going to try to show you in a few examples during this presentation. And also, then this is the part that we've been working the most in the last few months, and we're expecting to do a few releases in the coming weeks, which is cloud geoanalytics, which is not only we've passed the point of just visualization and just gathering insights from your data just by looking at it, but also we're making inferences and making you get conclusions, factual conclusions from your data using statistical analysis. And how do I move? Okay. Yeah, so introducing the product, I always like to show this map because you remember this this scandal that happened a couple of months ago with Ashley Madison. There was this website that was designed, I'm throwing someone's papers. that was designed for people to have an affair. So it was all a social network, sort of like OkCupid, but just for people who wanted to cheat on their partners. And they had a massive security breach where some hackers threatened them if they didn't close their website, because ethical reasons, they would release all of their customers' data, which would imply millions of people getting caught by the partners at the same time. And that's exactly what they did. So I actually have the map here because the most infuriating, well, it's not the most infuriating thing about them, but there's a curious thing that an allegation that not only the website was insecure, but also most of the female profiles were fake by a large margin. So this map created by some guys in Sevilla called Tecnologica showed which points, which places, which cities had less than 85% male population, which is already a pretty bad proportion for anyone looking for a female partner. But also, you see how many places, like Ashley Madison was trying to get, made a lot of fake profiles and still didn't get any market penetration. For example, here in Japan, because there was more than 85% male profiles, which we assume they're not fake, because, yeah. But we see that so that means that Ashley Madison succeeded in getting people to subscribe with those fake profiles. But in India and in Philippines, regardless of how many fake profiles they opened in the country, they didn't get people to sign up on the website, which I found pretty interesting. So going back to this thing, yeah. Yeah, so what we try to do is enabling people to tell stories. And at the same time, and this is the other side of the spectrum in our clients, gathering insights from the data by taking a look at them from a different perspective. This is my favorite project in CartoDB. I'll show you a live example. Yeah, no. So this is Global Forest Watch. A few years ago, there's this organization called the World Resource Institute, who has this product called Global Forest Watch. This is basically an animation application, well, an application that has animations that show almost in real time where forests and landmass that are covered by trees are being repopulated or depopulated. So I was focused in Spain, but if you see, so there's the blue points, which mean that the forest mass has been repopulated, and there's the purple points, which means that the points have the landmass has been removed. And for example, in Indonesia, there was this big problem where palm oil corporations were trying to scare tribes off their homeland by setting fire to the forest adjacent to the tribes, to where the tribes were located. And thanks to this tool, they were able to kind of unmask the corporations and publicly denounce those acts. And yeah, let's go back to the presentation. And this is done with no, I didn't want that. Okay. And everything is going wrong. And this is done thanks to a technology called Torque. Torque allows us to get a lot of data. This is millions and millions of points in a database. And without the use of WebGL or anything that depends on the GPU or is too technically advanced for many people to maintain and contribute to, we are able to display many points. Excuse me, I'm going to go back. You see that if I get close to this. This is not polygons or anything like that. This is individual points that have been collected by satellite imagery. And this is all possible because we have a server displaying a special kind of tiles that is different to the traditional map tiles. And I'll show you a bit about that right now. And because that's what I do in CartoDB, I do client-side rendering without WebGL. And I'm going to talk about what that means, client-side rendering. First, I usually like to speak about what client-side rendering involves. Rendering is a word that many people use, but it's a bit difficult to define it usually. So about 2 months ago, I had to give a talk to my school from when I was a kid about CartoDB. They invited me to give it, and I draw this. Basically, this is the process this is what I call rendering, which is just having some data, which is someone saying that there's a tree in Italy, and then there's a process in the middle that is called rendering that turns that into an image, and that to me is rendering. And the most important part of our client-side rendering stack in CartoDB is Torque. And Torque, as I was saying, is a library that allows people to get large amounts of data and display them not only in an aggregated way, allowing people to show loads of points, but also make them animated. And I love this example. This is something that came up when I started working in CartoDB. This is a guy from the Washington Post that got GPS tags on dummies and went to Alcatraz prison and released the bodies in the sea at different times of the day. And basically, this is the animation with Torque of where the bodies went following the different times of escape at different attempts in history. So to model what happened with them. So some of them just went off to the Pacific Ocean. Some of them, you see that as the currents, as the streams switch, they start to move a bit slower, and then they turn back. And actually, there's a police station here, and you see that some of the attempts go back to the police station. And yeah, and then there's some that go back to Silicon Valley and stuff. So I like this because it's a fun way of, because people usually in the mapping startup sort of environment associate Torque only with this, which is an example I really like, but people usually only see this. This is a Twitter map of people saying sunrise in their tweets. So you see that we've matched that with the time zone date. So you see that when the sun is rising, there's a lot of tweets saying sunrise. And especially in Europe, and you see now in the United States, everyone is saying sunrise. Yeah! And people associate Torque maps with this visualization, but it's not only that. It's also a very good way of visualizing time and making stories a bit more interesting by adding a spatial component to them. Yeah, I was talking about that. Yeah, that's a GIF that is way worse. There's a lot of non-profits use us to visualize a lot of points. For example, this is the I don't know if it sounds familiar to you, but the Ellis Act, and they tried to visualize all the San Francisco families that were forced out of their homes between 1997 and 2010. The thing is that I think the last time I accessed this, the map was down. Yeah, so you see that over time. You see, and there's at some point where the the act is approved, and the rhythm at which people are forced out of their homes goes up. And the size of the marker marks the amount of evictions in a single place. I like this one very much because it's in Germany. Where do birds go, depending of the time after sunset that they depart in, and the blue particles is the wind. There's a lot of really fun examples if you go to the CartoDB website. So there's a complexity with animated maps. The thing is that you can't use traditional data formats for animation maps because it's too heavy and too difficult to translate into graphics. The problem, for example, if you're familiar with GeoJSON, you see that it's too verbose a format, and it has too much data in it. For example, it has latitude and longitude information that implies that in the client, when the browser receives those data, it will transfer latitude and longitude into a pixel point. That's very inefficient if you want to visualize millions of points in a browser. There's another part that, you can't put 1 million points in a tile. That's impractical if you don't want to use a very complex solution like WebGL. And that means we have to use a very smart format that we call the data cube. Well, there are several variations of this name. There's tile cube, there's data cube, there's time cube, and in this case, it's data cube. Which means that we have, instead of a tile that maps are usually divided in, we have a cube, which means we add a spatial variable to the data we render. And then we don't have latitude and longitude, we just have X and Y points within that tile, which makes sense because PNG tiles are sort of the same. PNG tiles are files that just have pixel information. They don't have a latitude and longitude. That's only in vector rendering. And then there's in the server the server that serves these tiles. There's also another factor, which is the aggregation. When you ask for a dog data cube in the map, it will return an array of points that is not that doesn't correspond to latitude and longitude, but it will be binned in tiles. Sorry, not tiles. In columns and rows instead of being exactly that position. So it will aggregate the positions to be able to. Sorry, that's the thing. So instead of latitude and longitude, you get arrays of positions within a 256 by 256 tile. And this is a bit how the timing works. Instead of giving dates and giving, we give positions in time by calculating a number of steps with the starting date and the ending date. How are we doing on time? Okay. This also allows us, this is also all rendered in the client. We use we use CartoCSS, which is a language based on cascading style sheets that was invented by Mapbox, I think. You guys invented it? Yeah. But they're not using it anymore. And the way that it works is when you declare a talk map, a talk layer, you just set up a number of factors like how many frames do you want your animation to have, or and how much time does your animation take, and then the column that you want to set as time in your database, in your table, sorry, and the aggregation function. So what do you want to show? If you have a map of how many trains have crashed in the last year, I don't know why that example came to my mind, but I'm sticking with that. You probably want to aggregate maybe the number of I don't want to say number of casualties, the number of coaches that were involved or something like that. Then there's the talk resolution, which is what I was talking about. Instead of aggregating those, if you have millions of points, you don't want the server to return 1 point for each pixel, that resolution. In this case, for example, is 16, which means there'll be a point, the server will return a point value aggregated by the number of trains per 16 pixels, and that compresses the data a lot and makes using that data by the client, which in this case is a canvas renderer, much simpler. Well, this is a bit of how CartoDB is organized. You see, you see here Torque, which sits between the Maps API and the SQL API. Torque has to query the Maps API to get the tiles, which makes the SQL API convert, the tables and rows and all that data into a tile. And I just want to add this slide. I didn't make this one to locate our library within CartoDB. And the main, I'm the main maintainer of Torque and the whole client-side library stack in JavaScript. But I like very much that we have. I didn't do it, but we made Torque in a way that the renderer is very detached from the data. So anyone that is new to the library can get into can get inside the repo and just create a new renderer. And there's very nice examples of what people have done with this. For example, there's this data set of all the boats that sailed during the First World War and the loggings, like temperature, location, how was the weather, and collected by the Royal Navy between the 13 and 25. And using that aggregation technology by the server, we're not in this case we're not displaying points and locations, animations, but a guy from the solutions team in CartoDB converted that into this sort of heat map. There's also he also got the wind directions in those meshes and changed the renderer so that for each measure it would display sort of a needle of a canvas depending on the wind direction. And also, he made these are some tests with several variables. You know that I explained earlier that you had to choose one to aggregate into. This takes several. And these are some tests that are made by changing those points into ISO lines and getting similar values to belong to the same ISO band or ISO line. And also this is something made by Javi Santana, which is an animated Voronoi diagram. I'm not sure what the data set of this is. And this is the original. This is the original data set of the boats that were sailing during the First World War. This is one of the first examples of Torque that there is, and I suggest you open the repo and create a renderer. It's really simple. It's just if you have some experience programming, you can just there's just a method to receive the tiles and render them on the go. And yeah, thanks to all those people, Andy, Javi. Well, Andy actually ripped part of his presentation off for here, so a special thanks to him. Then Javi Santana Sterling and Aurelia Moser for helping with this. Also, I want to point out that we are hiring. So if you know anyone or you're interested in working in Madrid or New York, come talk to me. We have openings for pretty much every aspect of the company. Thank you so much.
I think pretty impressive. On the one hand side, we take a bit of time, but I think it was also quite useful to learn this, and it was really very impressive. One point, otherwise we continue with Mapbox. Okay, I think there's a lot of speed in these companies, really, and you can really see developments, how things are possible now which are so nice also, and it's something which is very impressive. So this will be Mapbox. I will pass it already. If you would like to do an announcement first, for instance.
Okay. Hello? Okay.
Take this away because it might be some.
Okay.
So let's go for Mapbox.
Hi, we're Johan and Daniel from Mapbox. Mapbox is a geo company that does maps, geocoding, and directions. Today we're only going to talk about directions here. If you want to talk about everything else, let's meet tonight. For drinking beers and other beverages. We'll have the announcement in the end, but yeah, let's go to Eschenbräu when Wherecamp is finished.
Hi. So my name is Daniel, and today I'm going to show you the state of OSRM. So basically, OSRM is the open source routing machine, and it's a routing machine, it's open source, and it's actually on GitHub, so you can just clone the repo, fork it, send pull requests, and there's actually a real community behind it. So we have the issue tracker and pull requests from the community. And what OSRM actually is this: it's incredibly fast routing on a global scale. So for example, you can see the routes here, they're changing instantly basically, depending on how you drop the marker. And this basically works on a global scale, so not just in Germany or Europe, but really on the planet. And then on the right side, you can see the instructions that we create. But this is done in sort of pre-process and in a sort of step after the route is generated. Okay. So what kind of data do we support? Mainly we support OpenStreetMap data, which means you just take your usual planet, you extract a graph from it, then you do some pre-processing, which takes quite a while, and then you can do routing on it. But we do not only support OpenStreetMap data, but also your custom data. For this, you have to basically convert it to the OpenStreetMap schema, which basically means respecting the max speed tags and so on, which is not too hard to do. Okay, so just a quick example of some OSRM users that are known to us, because after all, it's an open source project and you can just take it and go with it. So Mapbox is using OSRM in their direction stack. So this is basically OSRM for business users. So if you want the support, if you want availability, and so on, you basically just use Mapbox directions. Strava is also using OSRM for their routing. And so this is basically, you can see it, how they are using OSRM for their routes. Here, it's basically like a trip plan for athletes. And until recently, Uber also used OSRM for the ETA estimation. So every time you used Uber and you got some ETAs back, they were using OSRM. And there's a blog post out there, which is quite interesting, in which they explain how they build their own routing engine because of their own needs, which are quite special. Yeah, and if you have a mobile device and you use maps.me, this is actually OSRM on your mobile phone. So the maps.me guys, they figured out how to port OSRM on Android, for example. And then you can use OSRM directly on your phone without any server in between, which is kind of cool. So now to some OSRM features. So this is what you get if you do this kind of ST routing. So basically, you drop your marker at one point, you drop your marker at the second point, you get a distance back, you get a route back. This works with several profiles, and the profiles are what you see on the top here. So for example, here we have driving profile, a walking profile, and a cycling profile. And the profile selects, for example, the route types that you can take. You can see a park here, and the car profile isn't able to drive through the park. So this is kind of a filtering of your filtering on your planet, on your OpenStreetMap planet, for example. And depending on your profiles, you get different paths, you get different time of arrivals, and so on, different instructions. What OSRM is also able to do is elevation-aware routing. For example, you can put in your custom elevation data. You can use SRTM data, for example, because it's open source. It's just available. You can put it in, and then you can optimize your route with respect to the elevation. For example, in San Francisco, you don't want to route over hills because you want to minimize, for example, the elevation here, and you get like the best route, and these are the profiles right on the top, which is kind of cool. And in case you not only want to do ST queries, so basically from a start to an end, but also queries against multiple sources, multiple targets, so basically a distance matrix, you can use this feature called distance tables. And this is actually, this was a blog post by Johan about his favorite clubs in Berlin, and he used the distance matrix API to find the distances between basically all the clubs in Berlin. Yeah. Okay, and we heard about the traveling salesperson problem, and you can also do this using OSRM. So you can see just by dropping down markers, we can solve the TSP problem basically instantly. Yeah. Okay, so another interesting feature is map matching. So just think about the use case. You have noisy GPS traces, for example, from your GPS devices or from, for example, Strava, when they have runners, and you want to snap them to your geometry, to your network. And this is what map matching can do for you. It's trying to optimize, it's trying to find the most likely route for your noisy traces, and then you can snap it to the geometry. So in these use cases, they are quite, this feature is quite handy for use cases when you have noisy GPS traces. Okay, so now this was a quick overview of the basic OSRM features, and to make this scale, Johan is going to talk to you about deployment and DevOps.
Okay, so as Daniel mentioned, we're running OSRM to power the Mapbox Directions product, which is the hosted solution of OSRM. And we basically in OSRM have 3 steps. So the first thing is you have to procure your map data. And OSRM is based on the schema that OpenStreetMap gives you. So ingesting OpenStreetMap is the easy thing. If you have other map data, you can transform it to the OSRM schema. We then have to process, so it's not possible to just use the OSRM data right away, the OSM data. This is the hard thing about OSRM. It's OSM and OSRM, and we should change the name maybe. It's too hard. So you have to change the OpenStreetMap data to make it usable in the open source routing machine. And for this, we have to do a pre-processing step. And once this pre-processing step has generated a graph that is specifically usable for the routing, we can load this into a routing server to do requests against it. So the first thing with OpenStreetMap is, the very cool thing about OpenStreetMap that Steve Coast can probably attest to is every minute there's new changes. So you do a change, and within minutes it will be available for all OpenStreetMap users in the world. We are trailing this stream, and we are basically creating a new internal planet to use every minute. We mostly throw away most of the planets because we don't need them at that point, but when when we want to process a new routing graph, then we just use the latest planet. So the next thing is we have to process the OSM data. So OSM is, I think the current planet is 280 gigabytes. Uncompressed XML, it's 30 gigabytes as a protobuf. So we take that, we load it into a big instance. So we use 16 CPUs, 122 gigabytes of RAM. We run on Amazon Web Services, which give us these instance types. And it takes around 6 hours to pre-process for the car profile, 15 hours for the bike profile, and 23 hours for the walk profile. This is basically proportional to the amount of data that we have to be able to route on. And yeah, there's way more paths in the world than there is streets that you can drive your car on. So we process this from the OpenStreetMap data and then throw it into our API servers. We are running basically a whole stack of API servers for each of the profiles. So we have currently 4 instances per profile, running them in different regions, running them in different availability zones, so that the API never goes down, which, looking at my graphs, we're fairly good with. We're using the R3 2x large instances, 8 CPUs, 61 gigabytes of RAM, because we need all this RAM because we have to keep the whole world in memory. Again, we're not routing on cities, we're not routing on small geometries, we're routing the whole world. The example that Daniel showed with routing within Europe, we can route to Asia, we can route to China. There is maybe not a good use case for this, but there's definitely a good use case with the fact that we can do routing all over the world. We don't have to change for geographies there. The query time of OSRM is fast. So this is over a 2-week period, the average of the response times that we get from OSRM itself on the servers I just told you. And this is around 10 milliseconds. So it's milliseconds on the left scale, which means that it is super efficient. It is really, really fast. And the fact that it's so incredibly fast enables us to build all these other features above it that are the distance table, the solving the traveling salesman person, and building this in a way that we can also build a product around this that scales good enough that we can offer it for a good price. Done. Okay, before we go to questions, let's meet tonight at Eschenbräu, which is, after our ETAs, walking 8 minutes from here. And yeah, let's basically, when the happy hour here finishes, let's go over. It's possible to get food there, I guess, or you can bring food. You can bring food. Yeah, let's take it to questions.
Yeah, thanks very much first.
Hey, thanks very much for the interesting presentation. My name is Felix, and I have a question about car routing. So I think the most important objective for most drivers is time. So we're talking about fastest routes. And I'm wondering what kind of cost on the roads can your routing engine take into account? So can you take into account the fact that travel time is different over the course of a day, over the course of a week? And could you take into account real-time data for speeds on roads?
So right now we have basically different profiles, and these profiles have to be known before the pre-processing, which means you write your profile and then do the 6-hour or 10-hour pre-processing, and you can write your profile in a way to penalize certain streets, for example. In regards to real-time data, we are currently working on it, and there are basically 2 branches on GitHub right now that make it possible to do this. But it's not in a state that we can ship it, or it's not ready for production yet. But there are certain ways to basically do a trade-off between the query time. So instead of 10 milliseconds or 12 milliseconds, you go up to maybe 20 or 100 milliseconds, but then your pre-processing only takes a few minutes. And then you can do your pre-processing like every half an hour or every 50 minutes, which allows you to ingest real-time data.
Hi, Andrew Triffin of Navme GPS. We played with the routing, and we found that it is calculating very few alternative routes. Say London to Paris, there is just one alternative route, and London to Edinburgh, there is just one route. What is it related to? Why there are so few alternative routes? We compare it to our own routing, so.
Yeah, so we're using an algorithm that's called contraction hierarchies as the basis for OSRM. And it is very much optimized for creating the fastest route. And it is very hard to find alternative routes with that algorithm. We also currently doesn't have spent much time with it. If you want to spend time on better alternatives, we're happy to. It wasn't something that just fell out of the algorithm easily for us.
Okay, thank you.
Yeah, thanks for this next session. So we have another break now. And sorry for this change, but I think it's very interesting to approach, to discuss. We will have another session later on with other parts, as you've seen on the agenda. So welcome back after the break, and we continue. Thanks again. Very good.